So in this example, we are introduced to divisibility testing. And divisibility testing is just practical ways of being able to see if an integer is divisible by another integer. Our numbering system is based through multiples of 10. It's known as base 10. So the one divisibility test we are all familiar with is that when an integer ends in a 0, then the integer is divisible by 10. It's very simple and very straightforward. So for example, if we had something like 1,520 using the division algorithm, this would be 152. That would be the quotient times 10. That would be our modulus. And that would give us a remainder of 0. But suppose this was 1,526. We'd still have the same quotient of 152 with our modulus of 10, but this time we'd have a remainder of 6. So with this understanding, any integer that is divided by 10 will always have a remainder that's equal to its last digit. So with that same notion, we can conduct simple divisibility tests using 9. This is known as casting out nines. And one of the simplest ways of being able to determine if a number is divisible by 9 is if for letter A here, is if we simply just add up the digits of the number. And if the sum is divisible by 9, then the whole number is divisible by 9. So if we did 6 plus 7 plus 1 plus 4, that's equal to 18. Now we know that 18 is divisible by 9. So then 6,714 will also be divisible by 9. We can even continue this process with the result here. We could then say 1 plus 8. And that's equal to 9. And we certainly know that 9 is divisible by 9. So 6,714 is divisible by 9. Let's try B. 34,749. 3 plus 4, that's 7. Plus 7, that's 14. Plus 4, that's 18. Plus 9, that's 27. And of course, we know that 27 is divisible by 9. Using the same process as we did up here, we can continue this by adding 2 plus 7. And that equals 9. And of course, 9 is divisible by 9. So 34,749 is divisible by 9. Let's try C. 2,598,957. Now instead of going ahead and adding all these values up, it seems as though individual digits can be divisible by 9, or the sum of certain digits can also be divisible by 9. So what we'll do is we're just going to cancel out some of these numbers, thus the term casting out nines. So what I'm going to do is I have a 9 here. We can get rid of that one. I have a 9 here. I have a 7 here and a 2 here. That sums to 9. So I'm left with 5 plus 8 plus 5, and 5 plus 8 plus 5 is 18. And of course, we know 18 is divisible by 9, or we could also go 1 plus 8, which equals 9, and of course 9 is divisible by 9. So 2,598,957 is divisible by 9. Let's try D. That's 314,762,871. Again, we'll just cancel out or cast out nines or values that sum to 9. Here's a 9 here. I've got a 1 and an 8 right here. 4 and a 5, that sums to 9. 7 and 2, that's going to sum to 9. 3 and 6, that will sum to 9. 8 and 1, that will sum to 9. So we're left with 7. So 9 does not go into 7. But if we were to divide 9 into 314,589,762,871, it will have a remainder of 7. So when we have a value that comes out less than 9 and it's not divisible by 9, that's the remainder. And finally, let's try E. This is 72 quintillion, 206 quadrillion, 309 trillion, 719 billion, 290 million, 565,784. And we're going to see if this is divisible by 9. And if it's not divisible by 9, we can determine what the remainder might be. So we'll just cast out 9s. The first thing we could do is we could get rid of 9s. And we can get rid of 0s. And then anything that sums up to 9. Here's 7, 8, 9 right here. 6 and 3, that makes 9. Here's a 2 and a 7 right here. Here's a 7 and a 2 right here. That sums to 9. Here's 1 and 8. That'll sum to 9. And then 5 and 4. That'll sum to 9. So we're left with 5 plus 6, and 5 plus 6 is 11. And 11, that'll be 1 plus 1. That's equal to 2. So we'll have a remainder of 2. And when you think about it, 9 goes into 11 one time with 2 left over. So 9 does not go into this very large number. But if we were to divide it, it would have a remainder of 2.